Hi, I'm Darren, and welcome to Level Up EE Lab. In today's episode, I'll be continuing the repairs and modifications to this HT-40 amateur radio transmitter. I'll go through in detail all the modifications I'm planning to make, fabricate a small PCB to hold many of the new circuits, and finish with a demo of it working in both CW and AM modes. This is the second video I've made on this HT-40 project, and if you haven't watched the first one, I highly recommend you do so. In that one, I go through the background of the Hallicrafters HT-40 design and get the power supply working again. So today, I'm going to get right into the schematic and talk about many of the changes I'm planning to make next. Okay, let's start with the complete schematic. And what I've done here is placed it in PowerPoint so I can use the laser pointer tool to highlight specific areas. I'm not a big fan of PowerPoint. I think it gets way overused in my day job, but nevertheless, it does have some usefulness. Now once again, I want to thank Phil, amateur call sign AC0OB, for the excellent and detailed work he's published over the years on the HT-40. And just a comment, this is one thing I love about amateur radio. You can find an enthusiast for just about every single piece of gear ever made who will spend a lot of time studying it and documenting its history and coming up with good restoration or modification ideas. So thank you, Phil. Now, there are at least two versions of the electrical design. It appears Hallicrafters made some changes between the kit version, the HT-40K, and the factory assembled version. The model I have was made later in the production run, and the schematic I'm showing here represents that vintage. So if you're working on your own unit, you'll need to make sure you've got the schematic that matches your transmitter. In the prior episode, I went through the power supply and the changes I made to it, so I won't cover that stuff again here. What I'll go through next are the rest of the changes, and I'll zoom in on the affected areas of the schematic to make them easier to see. Alright, so in this view what I've done is zoomed into the upper left hand corner of the schematic, and we'll take a look at the oscillator and buffer stages handled by the 6CX8 tube. And I've also pulled in the 6DQ5 RF tube here as well, because its cathode control is shared with the 6CX8. Also notice that anywhere I've truncated the schematic, I'm showing those truncations with these blue arrows to indicate that the schematic continues elsewhere. Let's start at the oscillator. This rig will work with either a crystal or a VFO. If you put the control switch in the crystal position, what happens is the cathode of the oscillator side of the 6CX8 is available to be pulled to ground. Now there's one subtlety here. On the back of the unit there's a 4-position terminal strip, 2 of which are used for antenna relay control, for example, to control a coaxial relay to switch an antenna between the HT-40 and a receiver. But there's also an auxiliary control connection where you could use, say, an external keyer or a push-to-talk switch to transmit. I call this a subtlety because normally there's a small shorting wire here, and that's important to know because if you remove it or get a used unit where it's missing, you won't be able to key the transmitter by plugging in a key. If you follow the circuit, you'll see that the cathode on the oscillator requires this shorting bar to reach ground. If you are using a plugged-in key, it does not ground the oscillator cathode, so be aware. Let's move on to the modifications I'm going to make to this portion of the circuit, and again, all the mods I'm going to be showing here come from Phil's list of recommendations. I'm not incorporating everything he recommends. Some of those mods are quite extensive and require a lot of tear-up, so I've cherry-picked just the ones I want to try. So anyway, there are 2 components in this portion of the circuit that are replaced with different values. This RF choke is going to be replaced with a 1 millihenry unit instead of the 2.5 that's there now, and this cap that's 50 picofarad today, that's going to be changed to 39. Phil states that changing these values improves the spectral purity of the stage, and by doing it here, it reduces garbage from getting amplified later in the rest of the stages, and then ending up as spurious emissions. The larger section down here adds a couple of 6.3 volt double pole double throw relays, and they'll get their power from a very simple half-wave DC power supply by just tapping into the filament transformer to steal a few milliamps. So now, instead of the key or aux control grounding the tube cathodes, they'll now instead ground and energize these 2 relays. The first set of contacts, which I'm calling R1A, will now control the grounding of the tube cathodes. Now by itself, that would be adding pointless complexity, but that's not all these relays are going to do, and I'll explain more about that in the next 2 sections. Next, let's move on to the microphone amplifier and modulator section, and in this area Phil had quite an extensive list of mods he made, but I just decided to pick only the simpler ones. So that's what I'm doing over here with changing this side of the preamp. I'm adding these components here to the cathode on the 12AX7. Normally a cathode is just grounded. I'm adding an RC network here and reconfiguring the grid components as well, and adding an additional resistor and cap in series here. These modifications are all about eliminating high-frequency audio artifacts, which will improve the overall frequency response of this preamp section. And dealing with those issues here rather than later in the audio chain makes a lot of sense. And the second modification is adding relay contacts R2B here to the high voltage feed to the anodes of the 12AX7 and 6DE7. The reason for doing this is to depower these high voltage sections of these tubes when we're not transmitting. That reduces tube heating and prolongs tube life. A good thing to do, especially considering that nowadays some of these guys are becoming hard to find. And here's the third and final set of modifications. These are in the RF output stage, and the biggest change is in how the RF power is going to be measured. According to Phil, the existing factory circuit is not very accurate for measuring RF output power. So I'm going to reconfigure it to route some of the cathode current through the meter. That's a much more conventional way of deducing how much RF power is being transmitted. In this case, adding the 2.4K resistor and reconfiguring the connection to the meter will achieve that improvement. Now you notice here's R1B. That's the third set of relay contacts that I mentioned earlier. And what we're doing is interrupting the circuit when we're not transmitting. That will help prevent any overvoltage condition from ending up on the meter, but just as an added layer of protection, I'm also adding a 5.1 volt Zener diode across the meter. A few of the components are no longer needed, so I'm deleting them. And the final change here is just a subtle reduction to one of the caps on the screen grid of the 6DQ5, just to improve overall audio response. And there you have it. These are all the changes that I'll be making to this HT-40. Now, because the relays I've chosen here are designed to be used with through-hole printed circuit board construction, I've decided to design a simple board to hold them, and I'll also put some of the other through-hole components on there as well. Okay, so here's the PCB schematic and KiCad, and it is pretty simple. Here's where the 6-volt AC is halfway rectified into DC for the two relays. I'm using two 1000 microfarad caps only because that's what I had in the junk box, and I wanted a couple thousand microfarads of filtering. Each relay also has its own flyback diode across its coil, and the remaining parts here on the right are just the RC filter network for the key bias line, and the 2.4K resistor and associated filter caps for measuring the cathode current. And here's the layout in 3D, not much to it. I'm using through-hole components, more junk box content, and I've put the resistors vertical to save a bit on space. On the copper side, and yes, this is just a single-sided board and not double-sided, there's a ground plane, although with these signals it really isn't necessary, it's just more of a convenience in layout. Note that I did leave generous spacing around the R2B high voltage contacts. I don't want those traces close to ground or to low-level signals. And for additional isolation, I'm not using the second set of contacts in that relay. And here's the finished bare PCB, all ready to be populated. As I've shown in prior videos, I make most of my own boards using the toner transfer method. Doesn't it look pretty good? Now, these traces are wider than usual. They're mostly 1 millimeter wide, so the feature size is large. But notice the lettering and my logo. Those are fine details and they turned out crisp. On the chassis, there's this one open space right here that the new PCB will fit into nicely. So I added these two standoffs to hold the board in place and space it at a good height. And here's the board sitting on the standoffs. I'm going to mount it this way with the components on the bottom. That'll make soldering the wires to it easier and enables access for troubleshooting if needed. Check out the populated board. Now, one comment, I am exceeding the relay contact rating a bit for this application. They're rated for breaking 300 volts DC max at up to 250 milliamps current. The HT-40 high voltage circuit can be as much as 500 volts with no load, but the isolation voltage rating for these relays is a kilovolt, so all things considered, especially the low duty cycle, they should still work fine. Alright, here we are. I finished all the modifications except for one area to the underside of the chassis, and I'll talk about that here in a moment. But as I showed in the earlier video, here's the printed circuit board all mounted and wired in place. And just to kind of go over the highlights of the changes that I made, virtually every connection to the printed circuit board required some change to the wiring on the the chassis in order to connect it into the circuit. So you see here where I do have some wires that are running over to this area, and that's for the key and the key bias where I had to reconfigure that. For the RF power changes, there was a small terminal strip down in this area that I removed and then rerouted the power to come off the cathode of the main power tube. A couple other highlights wherever possible. Again, I tried to use little pieces of original type cloth covered wire, but where I couldn't find it, I just used regular 300 volt rated insulated wire, with one exception. For the high voltage circuit, since that's upwards of 500 volts, I do have some Teflon insulated wire, and that's this purple one you see right here, along with a piece of period authentic insulated wire right next to it. So just to try to maintain a high enough voltage rating was important. Some other items of note are when I connected the cathode voltage from the output tube over to the board, I used a short piece of jacketed, I guess you could say, cable, almost like a audio cable that has a braided shield on it. And the reason I did that, I noticed that when Hallicrafters built this radio, there's actually a similar cable that runs along the harness over to here. It's this orange cable right here that connects up to the key bias circuit, and I'm assuming they did that on purpose. They wanted that covered with a shield, probably to keep noise out of it, so I decided to do the same thing. It's not regular like 50 ohm coax or anything like that. I don't think it's that important, but I thought, well, what the heck, I'll just keep a shielded connection over to here for the cathode voltage sampling as well. And another subtle thing that I had to change is over on the meter switch. There's actually a change in polarity that's required with this new configuration where we're sampling that cathode voltage to determine the output power. So I did have to do some reconfiguration there as well. Now, I mentioned a moment ago that there were some modifications that I postponed, and they have to do with the vacuum tube V3. That's the microphone preamp. The reason I postponed those is when I looked at how this is actually constructed, there aren't any terminal strips nearby. All the resistors and caps are tied very closely to the tube socket, and that's normal for a lot of this construction. When I've worked on that type of construction in the past, it can be delicate because those old tube sockets, terminals can get brittle, and I want to hear what this radio sounds like first is what I decided, and that's why I'm postponing it. So I'll finish the rest of the modifications, I'll get it working again, check out the audio quality. If it doesn't sound satisfactory, then I will put those modifications in place. Can't forget the meter. So here's the new electrolytic capacitor that I put there to replace the old one, and tucked underneath it is that 5.1 volt Zener diode to help protect it against overvoltage. Okay, it is showtime. I've got the HT-40 connected to a few more pieces of equipment here to test it out. And yes, I did put the chassis back inside the case. That's from a safety standpoint. I don't want exposed high voltage right in the middle of my test setup while I'm manipulating controls and such. So always word of caution, if you're doing this type of work on your own, you're doing it at your own risk. There are very hazardous high voltages involved here. And like I say, trying to be safe by putting the chassis back in the case is just a common sense thing to do. So other equipment I've got, of course, I've got my Variac and dim bulb tester so I can watch the glow of this bulb as I fire it up. And I've got my Drake antenna tuner here. Now, I'm not using it for the tuner function. I'm using it for this watt meter. It's a fairly accurate analog watt meter so I can monitor just how much power is coming out. And of course, I'm going into my dummy load. Not going to be transmitting here, just going into the dummy load. And a classic straight key to be used to key the transmitter as I test it out. So what I've done as far as configuration, I'm going to put the transmitter on the standby mode. And it's on 40 meters because I've got a 7.04 megahertz crystal here that's right at the low end of the amateur 40 meter band. And what I'll be doing is turning this up slowly and watching for that dim bulb glow. Now it will glow somewhat. I expect it to have some glow there because it is going to be engaging all the tube heaters, and they do draw current, of course. But if this starts to glow very brightly, then I know I've got a problem here, and this will limit the current that goes into the unit, and I can shut it down safely and fix the problem. All right, so here we go. I'll put this in standby. And I'll start slowly bringing the voltage up. About 40 volts. I know you guys can't see it. It's off screen. I can only fit so much on screen at one time here. But trust me, the voltage is coming up. 70 volts. And I can start to see a glow there now. Maybe that's coming through on camera as I hit about 90 volts. And that's about all I'm going to get out of the Variac. I can't get the full 115, 120 volt AC because there's an appreciable amount of voltage drop here just by the bulb itself, and that's fine. So it's going to sit here for a moment or two at 90 volts, and of course I've got my fingers crossed that there won't be any magic smoke coming out, but I'll let this set for a moment or two, and if all goes well then I'll switch it over to full AC. Alright, I've let this set for a couple of minutes, so what I'm going to do now is flip the switch on my Variac dim bulb tester and take the bulb out of circuit, which means I'm going to apply the full line voltage to the transmitter. So here we go. Bulb goes dim. My meter, again, I know you can't see it off screen, is about 116 volts AC. And also, I can see through the top portals that the tube heaters look like they're glowing correctly. So all looks good there. So next step is I'm going to proceed with setting the grid current per the manual. Now the adjustment says to make sure that the crystal VFO switch is in crystal, because I'm using a crystal, and that the RF output grid current switch is in grid current, which it is. So I'm going to put this in tune mode, press the key, and adjust drive and look for a peak for the grid current. So here we go. And there's the peak, right around 4 point something on that analog meter. So that looks fine. And the final step in the tune-up procedure is to set the plate loading and plate tuning controls to maximize the RF output. Essentially what we're doing here is we're matching the resonance of the, in this case, the dummy load and the rest of the tuning circuits between the drive and the final output tube to be at maximum resonance for this particular frequency. Now, the procedure also says to maximize the meter when it's set to RF output, which I'll do. But I'm going to use as a referee my power meter and see just how close these track. I'm actually going to set, be watching more closely my RF power output because I trust that. I've used that for many years and I have a lot of faith in it. This not yet. I want to see how this meter actually tracks that meter. Now this is a step that you'd want to do fairly quickly because you don't want to be fiddling around with non-resident conditions. It's not good for tube life for sure. You can overheat the output tube and maybe even cause arcing. Worst case. So that's one of these procedures that you do want to go through fairly quickly. So here we go. I'll move the switch then to CW mode and hit the key. And again, I set this to RF output, so I'll be watching that meter as I adjust these two controls. And notice I do key up for a little bit, let it rest, and then try it again and get that peak there. So that peak is around 30 watts, which is about what I would expect, maybe a little more for this transmitter, so it's not too bad at all. Now, what I'll do on video, I'll go back and look how those two were tracking to each other. I couldn't watch them simultaneously, but I'll see if I need any maybe further adjustments to how this meter is set up. But it's working like it should. Okay, so moving on, there's a couple more tests I want to do on this HT-40, and the first one is to look at the quality of the CW transmission. And so I've got my Kenwood receiver set up here, and I'm also going to look at the AM mode as well. Now I'm going to be a little compromised in how well I can do that, and I'll explain in a little bit why I say that. But nonetheless, I'll start with the CW mode, and just a quick bit of background. I finally got smart on how to film in my lab here. I was having trouble with lots of reflections off of my parts bins, and dummy that I am, I realized just grab a big piece of masonite, put it in the background, and then I can position the lights wherever I want and hopefully get better quality lighting for when I'm working on the bench. So just a cheap and easy photographer's solution that I'm sure you guys that have been making YouTube videos for years know about. So learning as I go. Nevertheless, so what I'm going to do here, I've got the Kenwood set up on CW mode, and I put a different crystal in, 7.225 megahertz. I'm still on the 40 meter band. I switched it just because I wanted to see just on a different frequency how well the transmitter would work. And what I'm going to do here, I'm going to let the Kenwood warm up for about 30 minutes, and it's on now. And there's just nothing coming through because it's not connected to an antenna. And for sure, I'm not going to connect it to the transmitter. That would be stupid. I just have a length of coax in the back, about a 3-foot length that's connected to nothing. There's just going to be so much ambient RF emitted by the transmitter that it will pick up the signal. Now, what I want to look at is two things. First is there chirp on the CW transmission, meaning when I key it down, does it start at one frequency and end at another and sound literally like a bird chirping? And the second is to get at least some measurement of the frequency stability. Now, with a crystal oscillator, they're generally pretty stable, but nonetheless, just want to see how stable it is. And I know this is not very scientific, but nonetheless, it'll give me a general idea of how good this is. So I'm going to let the Kenwood warm up for about 30 minutes. And then after it's warmed up, I'm going to turn on the HT-40 and tune it, and then turn the video camera back on, and we'll listen to the first few CW transmissions that I can make, and then I'll let the HT-40 warm up for about 15 minutes as well, and then check it again, and just by ear see how stable it is. So here we go. Okay, I've completed the tune-up of the HT-40. It's been on for about 5 minutes, and let's hear what the CW output sounds like. Pretty good. Almost no chirp that I can hear. And again, I am transmitting into a dummy load. I'm not putting that signal out on the air. So that sounds good. What I'm going to do, like I say, is let this sit for about 15 minutes. Not going to adjust or change anything. And just see if there is any detectable frequency drift. So back in 15 minutes. All right, it's been about 15 minutes. So let's see how stable the frequency of the HT-40 really is. Not bad. By ear, I can't really tell a difference. Now, I chose 15 minutes. That's just arbitrary. I figure that's about the length of an average CW QSO. So certainly, if that's all it's going to drift, then the receiver on the other end really doesn't need to do much to alter his frequency. So that looks pretty good. So next step I'm going to do is reconfigure the setup slightly so that I can work this on AM mode. And I'm going to have a bit of a challenge here because these old rigs have a microphone connector that's not standard by today's microphone cable connections. They use a high impedance microphone, of course, but there's also this obscure connector, and I'll show an inset here in a video in case you guys aren't familiar with it, but it's technically called a Switchcraft 2501F, and you can find the connectors still, for sure. You can buy them online and whatnot, but trying to connect them to a modern mic that can work in high impedance mode is a bit difficult. So I'm going to jury rig something here and give it a shot. All right, I reconfigured the setup for AM mode, and as I mentioned, I did have to put together a claptrap connection here to get a mic going because I don't have that right connector. I have a Drake ceramic mic, and obviously it's got a connector that's not compatible, so just alligator clipping this to a clip lead that happens to have the right connector on the other end. So this is definitely a compromised connection. It's going to pick up some AC hum. But I think what I'm going to do, I'm going to put my mic over on the output speaker of the Kenwood, so try to capture as much of this audio as possible because I do have to turn the gain way down, and I have the microphone input turned down on the HT-40 as well. Otherwise, as soon as I key it, I'm getting a lot of feedback because the mic is so close to the speaker. So let's give this a shot and try to pick up something here. So here we go. Here's the HT-40 on AM mode. The audio is actually not very good, so there's a couple of issues that could be affecting that, and I'll put my mic back on and talk about them. All right, so several things I'm going to look at next. One is the microphone connection obviously is very poor. I need to get a cable that will connect better than just clip leads to this old Drake mic. Doesn't have the right connector on it, so that's definitely compromised. Second thing is I'm not 100% sure this old microphone is actually good itself. It's something I got years ago and I haven't used it for a long time, so it might be defective. And then the third thing is it gets back to those modifications that I put off to the microphone preamp circuit in the HT-40. It may be compromised as well and need those modifications. So a few things to look at in the future to try to make this work better on AM. So one thing I didn't mention when I was doing the AM test is you actually have to set these transmitters to make sure you're not over-modulating the output. And that's really the microphone gain input on the back of the unit. Now, what I'll be doing in a future episode on this project is adjusting that. And I do have a tool, actually a piece of equipment that makes that easy to look at the modulation. It's an HB610. It looks like a little oscilloscope, but it's made just for that type of operation to look at how well you're modulating. So I'll be doing that next time. And a couple other comments as I wrap up the video here. So the microphone, obviously I need to do something about that. That's just not going to work. So as luck would have it, there's a Hamfest this weekend I'll be going to. And Hamfest, if you haven't been to them before, they're like the predecessor of eBay. It is a garage sale for all things amateur radio and electronics, and they're a lot of fun just to see what people drag out on any given weekend to try and sell. So I'll be looking for either a microphone or appropriate connector while I'm there. Also in the next episode, I'm definitely going to want to wrap up the cosmetics on the case and get that painted and get this project done and get it on the air. And the microphone mods themselves, you know, I did say I put those off, and I do think I need to do those based upon what I'm seeing here. But I'll play with the modulation first and see if that maybe fixes the issue and actually get a decent mic. Maybe that's all it needs. Another thing I want to do in the next episode is bring my spectrum analyzer out. And if you've been watching my videos, you've seen I made this power tap, and that's perfect to use for a project like this because I'll be able to connect it to the spectrum analyzer and take a look at the output. And that's an area of interest for sure because these old transmitters weren't exactly very clean with their spurious output. So I definitely want to see what the out-of-band emissions might look like on this guy before I put it on the air regularly. So something good to check out. And then last thing I would say, I keep looking down because I'm one of these old timers. I like to keep notes on the project and just pieces of graph paper to keep track of the schematics as I work on them. Just put them in this old notebook. And I do have a lot of stuff stored electronically, but these handwritten notes come in so handy when you're working on a project. So I highly recommend you go old school when you're working on old equipment. So with that, that's all I have for today's episode. I hope you liked it, and I hope you watch the next episode in this series. And so until then, bye for now.